You're welcome. All right, so the title of these notes. I mean, have you come to one before? No, that wasn't like a slay moment. I just realized, like, you don't even know how enjoyable they are. They're a great time. Yeah, we enjoy them. All right, differential equations. We're gonna do.
I mean, I couldn't make it to the other ones because I don't have to.
Yeah, the other ones are better because Chick-fil-A. Yeah. All right. I did. I'll grab yours. Okay, we'll backtrack. All right, you guys ready? Okay. Basic definition of a differential equation. Martin, are you listening?
So I was company pal.
The basic definition, did anyone catch what the basic is?
Equation that contains an unknown, right?
But maybe what you might have noticed from the example problems. It's an equation that has like what inside of it?
Chain rule.
It has an unknown function, and does anyone know what shows up as the unknown function? It's the y value, right? Because functions are usually y equals. So when you see an equation that has like a random y in the middle of it, that is some function where if you could solve it for y, but we don't have enough information to solve it for y. Does that make sense? You guys remember like back in the day when we were doing the dy dx problems, and we had to do the chain rule with that because the y wasn't isolated, so when we found the derivative of it, we didn't actually know what the function was, okay? So that's what they meant by unknown function. So a differential equation is an equation that has x's and y's in it, and the big thing is it also has derivatives in the middle of the equation. So it's like a combination. It's an equation that has x's and y's and derivatives all inside of it, okay? So, and that's not like the formal math definition, that's just like if you look at it, that's what you can see. So we have like x's and y's and derivatives in the equation. And then normally when you solve an equation in math, you get like a point. Like if you solve a quadratic equation, you get like a point on the parabola. If you solve a linear equation, you get a point on the line. If you solve a cubic equation, you get a point on the cubic graph. If you solve a differential equation, do you get a point? No. You get a...
Yes or no.
Or I don't know.
What do you get?
A C.
So there was... Well, they used to C sometimes as a constant, but if you look back at the examples, how were some of the examples phrased? They would give you a function, and then they would say, yeah, so is a whole function a solution to a differential equation? So what does that mean about the solution of a differential equation? Is it a point? No, it's a function, yeah. So the solutions to a differential equation is a function, not a point. So this is like way different than what we've done before. So you're not going to say the solution to the differential equation is 5. You're going to say the solution to this differential equation is like y equals sine x. Or the solution is y equals x squared plus 2x plus 1, or something like that. Does that make sense? So a little bit different. Okay, we're going to try example number 5 now and see how it goes, and then we'll do some class problems to practice, because I think you guys will pick this up fairly quickly. This is just like going back and doing derivatives a bunch. And to me, it feels like kind of like a game because you're trying to match things up and see how they work together. So for example 5, it says verify that y equals c1 cos x plus c2 sine x is a solution to y double prime plus y equals 0. Okay. So when we look at this, does anyone know what the C1 and the C2 are talking about?
Derivative.
What normally goes in front of an equation?
The coefficient.
The coefficient. So this is the coefficient of cos, this is the coefficient of sine. They have different subscripts because they represent different numbers, even though they use the same letter. So it's not saying that this c and that c are the exact same value. They're coefficients, that's where they got the c from, and then one is for the cos and one is for the sine. And then this right here, this is your differential equation. So this is what we're trying to find the solution for, or we're trying to verify that it
What is
is.
our f?
So this is like f of x equals this stuff.
Okay.
So what it's saying is, if we find the second derivative of this and add it to this, then it should equal 0. That's what we're trying to verify. Okay, so my original function is that. So what I need to do is I need to find my first derivative so that I can find my second derivative, because the differential equation uses a second derivative. And that's what I'm going to have to plug back in. So how do I find the first derivative of this equation? The derivative of cos is negative sine. So the coefficient stays in the front, so we're going to have negative c1 sine x. What's the derivative of sine? Cos, positive cos, right? So plus c2 cos, right? So there's our first derivative. What's our second derivative? So the derivative of this is... Yeah, so sine goes directly to cos, right? And it stays the same sign. So it's going to be negative c1 cos x. And what's the derivative of cos? Negative sine. So it's negative c2 sine of x. There's our second derivative.
We just add the second derivative in the starting function.
Yep. So we're going to say second derivative plus the original function and we want to verify that it equals 0. Is that true? Yes. These two are opposite signs, so they cancel out. And these two are opposite signs, so they cancel out. So verify that it equals 0. So that's, yeah. So I kind of like the verify problems because it's like, yeah, I know the answer already. I just have to make sure that it kind of works out and makes sense. Okay. Sometimes when we're doing problems like this, they're going to mention what they call an equilibrium solution. So we're going to go ahead and write that, and then our notes will be done. So equilibrium solutions happen when there is no change to the function. That's why it's equilibrium. Oh, I was going to write that twice. No change, change. It could also happen where the derivative equals 0. That's where we're really going to focus today. And it could happen where there are horizontal asymptotes. So here is our last example. It's going to ask us to find the equilibrium solutions for dy dx equals y squared minus y. Do you guys remember what dy dx means? Derivative. So this is saying the way that y is changing as x changes. So one of the things we know about equilibrium solutions is they are where the derivative equals 0. So if we want to know the equilibrium solutions for this, and we know that this is the derivative, this function right here is the derivative, we just need to set it equal to 0 and solve. All right. So I'm going to write y squared minus y equals 0. And how do you solve an equation that looks like that?
You gotta do the d by dx anyway.
it's already a derivative.
I mean, no, I'm sure.
So how do you solve? So this is a quadratic. How do we solve quadratics? Factor or quadratic formula. Which one seems easier in this case? Factoring. Yeah. What type of factoring are we doing?
Y, take the Y out.
Yeah, take the y out. So we're doing a greatest common factor. So I have a common factor of y, and when I take that out, what is left over?
1.
Okay. So what are the two equilibrium solutions?
0
So
and
0
1.
and 1. So some of these problems, not on the worksheet that I'm going to give you, but some of the problems in the book, they might ask you for an equilibrium solution and then ask you for where something is increasing or decreasing. Do you guys remember how we look for where things are increasing or decreasing? So the derivative equals 0 where?
Oh, the sign thing, right?
Yeah, the sign chart, exactly. We're thinking sign charts. Where does the derivative equal 0? Max or mins. So if we remember back in the day when we did this, we would draw a sign chart. We would put these numbers, we're calling them equilibrium solutions now, but they're where the derivative equals 0. They're also known as maxes or mins.
So they should be the same.
Yeah, we would put them on a sign chart, and then we would look to see the numbers on the left, are they going up or down, to see if it's increasing or decreasing. So you're going to, some of that might be a little bit review because it's been a little while since we've done that. Okay, so we're going to practice some of these. So the way this worksheet works is you have a list of functions that are solutions on the left side. And then on the right side, you have a list of differential equations. And yeah, we're gonna try a few, and I'll show you. So the way that you're gonna do these is if you look at these differential equations, you'll notice that some of them are only first order differential equations. What does it mean by first order? Only has a first derivative. Some of them are second order. Some of them have the second derivative. So
we should just go through and find the derivatives of all of them.
Yeah, so you should go through these and find the first and second derivative of all of them, basically. So once I would not do that all at once because then you're not going to get to the part that's actually what we're learning today. So I do them one at a time. But once you do that, so I would write down like the first derivative of this and the second derivative of this. And then I would look over here to see what, like, kind of picture in my head what's going to happen if I plug it into these to see if it would actually work to equal 0. Some of them you're going to be like, yeah, that's clearly not a solution, and you can kind of ignore them. For instance, like this one down here has a square root in it. So if I find a first derivative or a second derivative and I don't see a square root anywhere, should I consider this as the differential equation that it works with? Probably not. So some of them you're going to be able to like think through and kind of ignore, but that's what we're doing here is we're kind of matching them up. All right? So for number 1, what is the first derivative of e to the negative 2x? So negative 2e to the negative 2x. In case you are brain farting on that, how did we do it?
You took the chain rule.
Yeah, so the derivative of e to the x is itself, right? So we took that, we just said, all right, the derivative is itself, and then we had to look at the exponent and take the derivative of the exponent, which was negative 2. Okay. How about the second derivative?
Do the same thing.
So we're going to take this, it would be 4e to the negative 2x. Yep.
Hey, Chris, you feeling it? Yeah.
I mean, he said it was positive, right? That was you, Chris, right? So there's a bet going on here that if Chris gets an answer right, James gives him $100.
Oh, great.
Hey, look, because I'll give you the answer.
All right, so now we have to look through. Now we have to look through our list of differential equations and see if we can kind of think about it. So if you look at the first one, it's saying take the first derivative and subtract off 2 times x times the original function. You think it's b? Okay. What do you guys think? Is that right? Is it b?
Negative 2e there.
Yeah.
So we've got the first derivative
Yeah.
plus 2 times the original function equals 0. Yeah, we agree with that?
Yes.
Perfect. All right, so the first one's B.
Hey, we're good. Good. We're trying to stay together.
All right, let's think about the second one. Our first derivative is
1/4 x.
What?
Nope.
1/3.
so.
Is it just
Oh yeah.
3x squared.
Yes, 3x squared e to the x to the third. So we took the e down, as we said the derivative of e is itself, and then the derivative of the exponent was 3x squared. Yeah, you guys like do that in your head. When I did this on my answer key, I like showed all my steps. Yeah, I took up a lot of paper to do this. All right, the second derivative would be what? 9x to the fourth, e to the x to the third. Okay.
You transferring that to the
Why would that be to the 4th?
Because you have this one, right? Oh, actually, no. I was not paying attention. What is this right here when you do it? You got one thing times another thing. What's that called? Product rule. Product rule.
No, man.
Product rule.
We don't know what that is.
I was just like following along with that. Okay, so product rule.
I'm putting it all down. I'm sorry. Putting the pen down, the pencil down.
This is why I would say maybe do your answers on a separate sheet of paper so you don't like make mistakes to conserve space. So it's the first one times the derivative of the second. What's the derivative of the second? 3x squared e to the x to the third plus the second times the derivative of the first. So that means our second derivative is 9x to the fourth e to the x to the third. So you guys were right on that, but there's another part to it.
Oh my god.
Why is there another one?
So
That's a little freaking ridiculous.
So we're not just, we couldn't just think of this as like the coefficient to the e to the x. That's kind of how we were thinking about it. Because it had the x, it was a product rule, so we did the first times the derivative of the second, plus the second times the derivative of the first.
I'm so sorry. Press these on first thing.
This is the second derivative. Alright, now to be fair, this is number 2, never mind. Does anyone, if you're looking through,
yeah, I was asking a question.
yeah.
So for so you just times both of them, like all of them.
So like we multiplied these two together, so we did 3 times 3 is 9, and x squared times x squared is x to the 4th.
Okay.
And we put the e right there. And then this one we just typically when you write you take the sub x.
Alright.
Right. Does anyone know if you are looking at it which differential equation it goes with?
Is it F?
It's F.
We're thinking it's F? Okay. So let's look at it. Now what made you think that maybe we needed to do F? Like what was your clue?
The 3x squared.
The 3x squared, yep. That was, when I was looking through that 3x squared is what made me notice F as well. Yeah.
But
So,
are we going to do F and find out that it's wrong?
yeah. No, I'm pretty sure F is it. Hold on, let me check my answer key. I forgot to pause the video, so it just ran that whole time.
That's all right.
Alright, so second derivative is 9x to the 4th, e x to the 3rd, plus 6x e x to the 3rd, minus 3x squared times the first derivative, which was 3x squared e x to the 3rd. So we did the hard work already. We did our derivatives, and now I'm literally just plugging it in. So my second derivative's right there. I plugged that in first. And then I have negative 3x squared multiplied by my first derivative, so I'm plugging that in right now. And then I've got negative 6x being multiplied by the original function, which was e x to the 3rd. Oop, e to the x to the 3rd. Okay, what do we see?
So you would still have the first two cancel out, but the 6 to the xy.
Wait, so these cancel out, right? And then these cancel out. So it is true. F is definitely the answer for number 2.
Yeah.
Okay. So if you go through and you do your first derivative and your second derivative and you just can't see it, ignore that one. Come back to it later because you're gonna, each of these only matches up with one differential equation. So just wait until you like narrow it down somewhere that you can come back to it. When I did number 3, I could not see the solution right away. It took me a while to find the answer to number 3. But some of the other ones are like really obvious. So that's what we're gonna start with. Yes, sir.
This is how all the problems.
Or could you like
For the whole unit, I'm not sure. I haven't looked that far ahead. Was that a good answer?